Hey, welcome back to Fan Mama Physics. In this video, we are going to do another graphing problem example, which is going to be a little bit different than the last one you did. Notice this particular example, it gives us two displacement distance graphs. There are two of them. We're not giving a displacement time graph, so we're going to have trouble with the time aspect. But at least the question here tells us what the snapshot of the wave looks like at certain times. The first one, it was taken at t equals 0 milliseconds. The second one was taken at 4 milliseconds. So 4 milliseconds afterwards, this is what the wave looks like. So let's take a look at these questions. First of all, what is the amplitude of the wave? And if you take a look, it doesn't really matter which graph you use. Both of them are snapshots of the wave. Both will communicate your amplitude, which is just from the equilibrium position to the maximum displacement of 1 millimeter. Okay, next up we need to find the wavelength. Now luckily we're given the displacement distance graph, so we can find the wavelength. The wavelength would be either here to there. It doesn't matter which graph you use, both are representing the same wave. From there to there, and you can pretty much see right there, this is 6 centimeters right there. That's a wavelength, okay? 6 centimeters, and don't forget you need to read the units of your axes. So some students I know are going to write meters instead. Okay, so this is where it gets a little bit tricky. The questions C and D. It requires you to think about what the wave is doing. So let's take a closer look at these two waves. The question is asking for the maximum possible period of the wave. So before tackling question C, the important thing that we have to fully understand is the fact that if I have a single particle on my wave, as it makes one complete cycle back and forth, all the way down, all the way up, it would have traced exactly one wavelength, meaning my wave would have traveled the distance of exactly one wavelength. Because imagine as it is moving down and then moving back up, it has traced one exact wavelength. So the association between one wavelength and one period is very important. The other thing we want to understand is the fact that to maximize the period, it means that my particle has gone through its entire cycle taking the longest amount of time. If it has done this, then imagine my wave would have gone, more wavelengths would have gone by. And we don't want that. We don't want many wavelengths to have gone by. We want less amount of wavelengths to go by because we want the maximum number of periods. The maximum period. So the particle would have gone very, very slowly. My wave, the top of my wave, not many wavelengths would have gone by. So those two pieces of information we need to think about as we're doing this one. So for question C, this guy over here, I'm going to use a crest to track how far this crest has moved from graph 1 to graph 2, because crests are easier to observe, to track, as opposed to the middle points of every graph. You can use a trough. It really doesn't matter if it's crest or trough. So if you take a look at this crest, and knowing that the wave moves forward, moves towards the right, so that's this part here, then we kind of have to think, well, if this guy is moving forward, then this particular hump could either be here or here. But remember what we said earlier. We said that we don't want too many waves to have passed by because we want to ensure the maximum maximum period for one complete oscillation. So this hump shouldn't have moved very far at all. So we can rule out this one. We can also rule out all the many humps down the road because that would mean that my particle would have oscillated very many times shortening the period, which we don't want. We want maximum period. So for this hump to go from there to there, it took 4 milliseconds. So here to there took 4 milliseconds. And then what we want to do next, if we want to take a look at the span of the wave that has gone by. So if you take a look at this part, comparing where the wave was before, the wave was roughly at the 0.5 centimeter mark and has only traveled over here, which is this is about what, 4.5? 4.5. Yes, about 4.5 centimeters. So only this much of the wave has traveled 4.5. Has traveled that far, and it's only traveled for half the wavelength amount for the particular wave. So this particle only moved through half of a period. Remember, we're associating the one period. A particle moving through one complete period is going to trace out one wave. This particle has only moved through half of a period. So it's only gone from the top and has moved all the way down. That's only half a period. So we know that this time here is only half of a period. So to get the full period is going to be 4 milliseconds doubled, giving us a total of 8 milliseconds. So 4 milliseconds times 2, this is going to be 8 milliseconds. Okay? So that's the hardest part of this question, because you kind of have to think about what this wave is doing. This hump only moved through half of a wavelength, meaning my particle that's oscillating would have only gone through half of a period. Therefore, to find the full period, you have to double the amount of time that took, which is the 4 milliseconds, giving us a total of 8 milliseconds. Next question is D, the lowest possible wave speed. So you're thinking, wait, one's asking for maximum period, one's asking for lowest wave speed. What is going on? So if you take a look at the wave equation, I'm actually going to use wavelength over period instead. Now, if you want to maximize the period, meaning this number is going to be very large, that's going to make this number over here very small. And that's what we want. We want the lowest possible wave speed. So that's the only way for us to get the possible lowest wave speed is to find the maximum period of the wave. So what we did in C, we're totally going to be able to use it for question D. So our wavelength we know is 6 centimeters. Our period is 8 milliseconds. So then we just have to make sure that after we calculate this, we leave it in meters per seconds. So the easiest way to do that is to convert 6 centimeters to meters, 0.06. And then the 8 milliseconds is going to be 0.008 seconds. Okay, if we convert it to seconds, we take the top divided by bottom, we get 0.06 divided by 0.008. It's going to give us 7.5. See? It's so easy to make some mistakes. 7.5 meters per second. Hey, and that was a question. So yes, question 2 is a little bit trickier than question 1. Question 1, you just analyze a graph and do your readings. Except question F, that's a little bit trickier. This one, you really have to, this requires a stronger understanding of how a wave moves. So I would recommend, if you struggle with this question, try to find similar questions in your textbook, online, or ask me. So hopefully you found this video helpful, explained a few things, and I wish you good luck with the rest of these questions. They're very tricky. And Fat Mama Physics signing out.